us continue our discussion on the half-wave rectifier. So in a half-wave rectifier, for an applied voltage of this kind of sinusoidal signal, you get only the positive peaks remaining, positive half cycles remaining, and the negative half cycles are flipped, and you get zero waveform here. And as I explained earlier, so the half-wave rectified waveform waveforms can be expressed as a DC component plus some alternating component, and the component of interest is the DC component when you like to use this as a power supply, and we try to attenuate the alternating component. Okay, so now let us analyze and see how much is the DC voltage present in the half-wave rectified waveform, and let us also see how much is the AC component is there, because we should have an idea about how much is the unwanted component in your waveform. And we being engineers and scientists, we should have a quantitative idea about how much is this. So let us carry out the analysis. As I explained, the DC component is the average of the waveform of the half-wave rectified waveform. Therefore, how do you get this component? If you integrate the voltage Vm sine omega 0 t over half period, where this is the time period, because for every full cycle you have one half cycle present, and average over one cycle is equal to average over two cycles is equal to average over any integral number of cycles. So let us find the average of the waveform within one cycle. So average of the waveform over one cycle is equal to averaging over 2 pi radians, and the integration of this waveform from 0 to 2 pi radians boils down to an integration of 0 to pi, because pi to 2 pi the integration is of 0. So therefore we will be integrating from 0 to pi, so dt, and 1 by 2 pi here. There is a problem here. If I integrate sine theta with theta, the integration is from 0 to pi. If it is with respect to time, I have to integrate from 0 to t by 2. It is one and the same. Therefore, the integration is this. This is the DC component, and while averaging out, I will be averaging it over a time period of 2 pi. So this is the average. So if you do this integration, so you will find that this is equal to Vm by pi. This is what you get. So if this is Vm is say 10 volts, so the DC component, the average component you get would be 10 by pi. It is around approximately 3 volts. Okay, as the DC component out of 10 volts, and the remaining is the AC component. So how do you measure the AC component? By average. The average of an AC component is 0, so it doesn't give you anything. We measure it by RMS value. Okay, so if you determine the RMS value of the waveform in the same fashion, you will determine the AC component also. Okay, so if you determine that AC component, you will find that the RMS component is equal to Vm by 2 into square root of 2. So this is what is the root mean square value of this signal. So how do you determine it? By squaring it and averaging it over one period, again you will get the RMS value. Okay, so you please do it as an exercise, as a homework exercise. So this is the AC component and this is the RMS component. Any questions on this analysis? It is complete RMS value of the half-wave rectified waveform, not after subtracting the DC component. It is including that. So any other question? Now let us discuss about a full wave rectifying circuit. Normally, the rectifiers are associated with a step-down transformer, and in some rare cases, a step-up transformer. We supply the primary input from the mains, which is a 230 volt mains typically, and this is the transformer. For small voltage sources, we use a step-down transformer and take the supply, small AC supply, rectify it and get the DC voltage which we want. Now with the transformer included, the circuit looks like this. So a full wave rectifier, this is several circuits configurations are possible, while I am giving one of them here. You use a center tap transformer in the secondary and connect the load resistance over here like this to this arm and connect another diode in this fashion to this point, and this is the load resistance RL, and the output across RL, what we want, the output we want across RL, so is this V0. And if we consider this as the ground point, so the voltage of this point is what V0 above the ground point. So typically this is how we use it in circuits. So this is a full wave rectifying circuit. When you turn on the mains supply here, you will get a Vm sin omega t over here, and you will get another Vm sin omega t over here. So that's what a center tap transformer give you. If it's a 20 volts transformer, it will give you 10 volts here and another 10 volts here, because the tap is in the middle. Okay, so this transformer is like that. Now so this kind of AC applied here, like a sinusoidal AC applied here, let us see what happens to the circuit. For the positive half cycle, you have a small positive sinusoidal voltage appearing here and the same amount of positive sinusoidal voltage appearing here. Now for the positive voltage appearing here, what happens to this diode D1? So D1 is forward biased, and with the same amount of positive voltage appearing here, what happens to D2? So D2 is reverse biased because the anode side is connected to the negative point. Hence, so D1 conducts and D2 goes off during the positive half cycle of the mains. Therefore, this is like an open circuit because this D2 doesn't conduct. Therefore, it is like an open circuit, and what is applicable is only the upper half of the circuit. Hence, for the positive half cycle here, this diode acts like a half wave rectifier. It conducts and it transfers the input voltage to the load. Hence, across the load you get this kind of voltage during the positive half cycle. And the circuit gets completed like this. Whereas this side it is like an open circuit. Almost no current flows through this side. Now during the negative half cycle, well, this voltage gets reversed, and the situation you have here is this is positive, this is negative, and this is positive, and this is negative. Because this terminal, you have a negative half cycle, that means this is negative compared to this, and this is negative compared to this. Therefore, so this side is positive compared to this side, and this side is positive compared to this side. Then what happens is D1 is reverse biased and D2 is forward biased. Therefore, D2 conducts and it transfers this voltage to the load, and so D1 is off, D1 doesn't conduct almost, and as a result it is like an open circuit. Therefore, what is applicable is only this lower half of the circuit. Therefore, now this D2 conducts, it transfers this positive, negative, this voltage to this RL in the same direction like what happened in the previous half cycle. Therefore, the voltage that is appearing across RL would be like this for the negative half cycle of the input. With the positive half cycle contributed by through the diode D1, the negative half cycle is contributed through diode D2, but both appear in the same direction across the load resistance. Hence, this is the kind of output voltage you get across the load resistance. So this voltage waveform is known as a full wave rectified waveform, and this is known as a full wave rectifier. So the advantage with this circuit is that both the half cycles are the negative half cycle is also reflected to the positive side, and you have the full wave form appearing across the load resistance.
Sir?
Yeah.
So, but in case of the input voltage, the peak values were 20 volts. We will be getting 10 volts in the output.
It depends on the transformer. Say you want 20 volts peak, you use 20, 40 volts transformer.
But that will be half.
Yes, yes, that's it. So that is immaterial. You can use a transformer, appropriate transformer, you get the same voltage required. It's not that the transformer is under question. It is the voltage is under question, we use a suitable transformer for it. So the advantage is this kind of a waveform, that's what you get. Now let us analyze this circuit. So what is the DC component? Please note that in this case also the peak voltage is equal to Vm. When the diodes are ideal, the peak voltage is Vm. Okay. Then what is the DC component you expect now? In the case of a half wave rectified waveform, we were integrating that half cycle over one full period. So that integration was over only 0 to pi. It comes to the area of one half cycle but divided by 2 pi. But now when you integrate this over, when you take the average, in fact the average over that pi radians or 2 pi radians or 3 pi radians or 4 pi radians, where pi or 2 pi amounts to the radian frequency in this waveform, okay, is all the same. So now the averaging is over. The same area would be averaged out over pi. Hence, you get the DC component as 2 Vm by pi instead of Vm by pi. you get a DC component which is twice that of the half wave rectifier. So this value is 2 Vm by pi. That is the amount of DC voltage you get in this case. So which is definitely twice that of the half wave rectified waveform. And what about the RMS component? RMS component is determined by squaring the waveform. Let me repeat. In the case of a half wave rectified waveform, so this is the waveform. We have to square it first. When you square it, the waveform would be like this. And when you integrate it, squared value when integrated, so you will get the area. And when you divide it by 2 pi, you will get the mean square value. And after dividing it by 2 pi, you get the mean square value. And square root of this is the RMS value. The same way you can determine the RMS value of full wave rectified waveform also. And you will get VRMS as Vm by root 2. Vm by earlier it was Vm by 2 root 2, and in this case it is Vm by 2. So this is the RMS value. The squared value is halved, is doubled now. Mean square value is doubled in this case because the area of the square waveform when integrated is getting doubled. RMS value is under square root. Therefore, whatever is the RMS value you have previously, this will be 1 by square root of 2 times of that. Therefore, Vm by 2 is the RMS value here for full wave rectified waveform. Is it clear? Okay. The area after squaring, I repeat, the area is now doubled. The squared value when integrated, you will get 2 times. So square root of that would be 1 by square root of 2 times. Therefore, instead of Vm by 2 root 2, now you will get Vm by 2 as the RMS value of this waveform. Oh, there is a mistake here. There is a mistake here. Let me correct it. This would be Vm by square root of 2, and for half wave rectified waveform, it will be Vm by 2. I'm sorry for this mistake. So please note this. This is Vm by 2. Vrms is equal to Vm by 2 in the case of a half wave rectified waveform, and this is equal to Vm by square root of 2 in the case of a full wave rectified waveform. Now let us discuss about another circuit which is very widely used in rectification, another circuit for full wave rectification. So that is a bridge rectifier. This is a transformer, and this is the main supply, and then a bridge circuit with the diodes is with the diodes connected in this fashion is used. So designating this diode as D1, this is D2, D3, and then D4, and treating this point as the ground point. So we connect the load across this. So this is the output voltage, and we apply the mains here. Now during the positive half cycle, so this side is positive compared to this, and as a result, so D1 would be forward biased and D2 would be reverse biased because its anode is connected to the negative most point. So D1 is forward biased, and this voltage is transferred to the load on this side, and the current goes through this load resistance in this fashion. And this current passes through this diode D4, I mean D3, and the circuit is completed. That means it is like this. Between the supply you have diode D1 and load resistance RL, and you have diode D3 connected in this fashion, and you have this input applied like this. Secondary output of the secondary of the transformer is applied like this. So in this situation what happens is both the diodes are forward biased and they are in series, and rest of the voltage is passed to the load resistance RL. So in this process, please note that diode D4 is also under reverse bias. Diode D4 is also reverse bias because its cathode is connected to the positive most point. Okay, so D2 and D4 do not conduct, and T1 and D3 conducts are forward biased, and the rest of the voltage is applied across RL. Therefore, during the positive half cycle, the RL gets the positive half of the cycle. When during the negative half cycle, so this is the situation. So this side is positive compared to this side, and since the anode is connected to the negative most point in the circuit, diode D1 is reverse biased, and D3 is also reverse biased because the positive most point is connected to its cathode. Therefore, diode D3 is also reverse biased. Hence, the circuit and D2 and D4 are forward biased. Now, this positive supply is applied to RL through D2 and so D4, like in the same fashion, like here. So the negative half cycle is applied in the positive direction to the RL through D2 and D4. So this time it is D2 and this is D4. Hence the negative half cycle is passed to the load resistance in the positive direction. Therefore, you will have this kind of voltage appearing across the load. Hence, you get full wave rectified waveform over here. And the analysis is the same analysis which we obtained which we made for the full wave rectified waveform is applicable. Okay. So this is applicable when the diodes are, the reverse biased diodes are reverse biased such that the avalanche breakdown doesn't occur. That means the reverse voltage applied across the diodes is less than the avalanche breakdown potential. Therefore, how much reverse potential that is being applied across the diodes is also of interest to the circuit designer. Let us now look back at the circuits and see how much is the peak inverse voltage or peak reverse voltage, so that is being applied in each one of these cases. In this particular case, let us first consider the half wave rectified waveform, and let us see how much is the peak inverse voltage of the diode. How much is the peak inverse voltage here? Peak inverse voltage is, and what is the maximum amount of reverse potential that is applied across the diode? So naturally, it is during the negative half cycle, and that is equal to Vm. So the peak inverse voltage in the half wave rectified waveform here is equal to Vm. As a circuit designer, you should see that the breakdown potential is greater than Vm. Otherwise, it doesn't work like a rectifier. Now let us look at the full wave rectifier shown here. What is the peak inverse voltage applied across the diode in this circuit? Well, during the positive half cycle, we have seen that. So this voltage is Vm with respect to this. If this is ground 0, so this side is plus Vm, right? And this side is, in the case of an ideal diode, this load has plus Vm across on this side of the load. And this side is ground, that is 0. What about this diode? So this side is minus Vm compared to this ground, and this side is plus Vm compared to the ground. Therefore, how much is the peak inverse voltage across D2?
Twice 1.
So it is naturally 2 Vm. During the positive half cycle, D2 has a reverse potential of 2 Vm. And the same thing happens with the D1 during the negative half cycle. The symmetry. Therefore, the peak inverse voltage in this case is 2 Vm. If you are interested in a 12 volt peak voltage at the output of the rectifier, you should select a diode with a breakdown potential which is more than 24 volts. Now let us see what is happening in this circuit. So what is the peak inverse voltage in this particular circuit? During the positive half cycle, as we have seen, so D1 and D3 are forward biased, and if this point is grounded, is a ground point, so with ideal diode, this is also almost at ground potential, right? So this is Vm, and with ideal diode D1, so this is Vm, right? Therefore, what is the inverse voltage across D2 now? This is 0, this is Vm, the peak inverse voltage is Vm. And what about D4, which is also reverse biased? This side is 0 volts, and this side is, so this side is Vm, with this as positive. Therefore, the peak inverse voltage across D4 is also equal to Vm. And the same thing happens with D1 and D3 during the negative half cycle. For in this circuit, the peak inverse voltage is equal to Vm, unlike in the previous circuit. Therefore, the advantage with this circuit is that the peak inverse voltage is equal to Vm, which is half of that of the previous circuit. Hence, if you are interested in, say, a 12 volt peak full wave rectified output wave voltage, you have to select a diode whose avalanche breakdown potential is more than 12 volts. That is sufficient, unlike in the previous case. Okay, so this is the advantage of the bridge rectifier circuit. Any questions so far?
Any other advantage?
this is one advantage. The other advantages are that two of the diodes are in series, and rather it is a disadvantage. So two diode forward potentials get subtracted from the waveform. Okay, so that's all. I mean, there is no other advantage. The load or the power dissipation do not get changed. Well, the analysis we have carried out so far is with the assumption that the diodes are ideal. If the diodes are not ideal, so what do you expect? In simpler terms, if the input peak voltage is Vm, output peak voltage cannot be Vm. It would be less than Vm by how much amount? By an amount equal to the diode potential, which is of the order of 0.6 to 0.8 volts. If the current drawn is very small, it is close to 0.6 volts. If the current drawn through the diode is very large, it may go up to 0.8 volts. And as a result, there will be some amount of voltage difference. So let us do the analysis with the actual practical diodes by taking the practical diodes into consideration. So accurate analysis. So during the positive half cycle, so this diode, let us do the analysis for a half wave rectified waveform. During the positive half cycle, the diode can be replaced by its equivalent circuit with its forward resistance RF and the V gamma here, and RL connected like this. The load resistance connected like this. So this is the output voltage, this is the input voltage. So let us slightly change the notation here. Let the input voltage be V0 sine omega 0 t as the input voltage. And the output voltage is, let us say, with peak value is equal to Vm sine omega naught t. So what is the difference between V0 and Vm? So the difference is V gamma plus, if the diode peak current is Im into RF, the voltage drop across the diode is equal to V gamma plus RF into Im. And the output voltage is Im into peak output voltage Vm is Im into RL, where Im is the peak current. Okay, so we know that the output is also output in this case is also almost sinusoid, but half wave rectified with the peak value equal to Vm. So we are now determining Vm in terms of the input peak voltage V0. So the difference between these two is this V gamma plus this diode drop. This is diode drop actually. This is diode drop. And this diode drop is that V gamma about the 0.6 or 0.5 volts plus small additional drop, which depends on the load current. So since we are interested in the peak value and rest of it is sinusoid, we are interested in the peak value here. So let us determine that. So this peak value is equal to the peak value of the input V0 minus RF into peak value of the current minus V gamma. That means the diode drop is to be subtracted from there. And after subtracting, we get the output as Im into RF naturally. Now by solving these two equations, like Vm is equal to V0 minus V, that is V gamma plus RF Im, So by solving these two equations, we can determine Vm. How much is Vm? Please substitute and tell me. So Vm naturally is, it is very simple. This peak voltage V0, look at this. This peak voltage V0 minus this V gamma. That voltage is the net drop across RF and RL. That means that voltage V0 minus V gamma is getting divided between RL and RF. Whatever appears across RL, so that is it is V0 minus V gamma. This is getting divided across RL and RF. So therefore the voltage drop across RL is RL plus RF. So this is the result. This is Vm. Peak value of the output voltage. So practically, say Im is say of the order of say 100 milliamperes in a typical application, and say RF is 1 ohm, and RL is say 1K. The drop due to this RL plus RF. So this is RL by RL plus RF. So this division is 1000 by 1001, which is almost 1. And that V0 minus V gamma, which is of the order of 0.6 volts. So this drop is almost 0.6 or 0.7 volts, and whatever is the remaining voltage goes to the load. Okay. So with the Vm now known, what is the DC component? DC component is Vm by pi, and the AC component, the RMS, its RMS value is Vm by 2, and the same analysis is applicable for the full wave rectifier also. Full wave rectifier with the two diodes. In this circuit also, the same analysis holds good. The relationship between input V0, peak value of the input V0, and the output voltage, peak value of the output voltage Vm, is the same. Same expression holds good. Well, when you apply it to the bridge rectifier circuit, please note that you have two diodes coming in series, and as a result, you have to consider two diodes drop. Hence, if the peak value here is V0 on the input side, what is the peak value on the output side? So it is obviously V0 minus, this time you have two V gammas, and that is divided between RL and two RFs. Therefore, it is RL by RL plus 2 RFs. The analysis is so this is accurate analysis. It's not difficult at all. We have made use of the piecewise, the equivalent circuit, which is derived from the piecewise linear characteristics of the diode for the analysis here. That is the beauty of the equivalent circuit. We have not used the exponential equation. We have simply used simple resistance and then voltage source as the equivalent, and then we have done the analysis. And this is accurate enough for our practical purposes. Okay, so this shows why equivalent circuit is important for us. Any questions so far? Questions? If any problem is given, it should not be difficult for you to solve it on this question. Now, if you want to design it, the design problem is inverse to the analysis problem. How do you design it? If I want a DC value, average value of 10 volts, and I use a full rectifier, what should be the peak value of the output voltage? DC value is equal to 2 Vm by 2 Vm by 5. So I should take a peak value of, that's it. So that is the value. And so that is the transformer secondary. If you add the drop across the diode, say about 0.7 volts, whatever accuracy you apply, after all it varies between 0.6 to 0.8 volts. So add it. So that will give you the secondary voltage of the transformer. And what is the primary voltage of the transformer? Power mains. This 230 volts RMS. 230 volts RMS. The peak value is 230 into square root of 2. That is the peak value. And if that is the peak value, you know the secondary side peak value. What is the transformer ratio? Okay, that is the transformer you need. And does the design end there? So you will go and ask in the shop, I want a transformer with turns ratio equal to 16.567567 in the market. Do you get a transformer of that type with 16.567? Unless you wind your own transformer or ask some manufacturer to wind it for you, specially design it and wind it for you, you will not get it. So why? Because in the market also you have only some standard transformers available with some standard primary to secondary ratios. So now the next, therefore, when you design, you should see what are the available transformers in the market and take a voltage and see that you get a particular voltage with those transformers and design your supply for that voltage. And if you want some kind of vague power supply, well, after getting the output, you have to divide it through a series resistance or take some action and then apply it to your circuit. And if you go one step below, for the manufacturers themselves to make such circuits, they should take the standard values available in the market. So whenever you buy a system, they should not say that I want a voltage of something like 14.67 volts as my supply. So they should also say that, well, I want a 9 volt supply or 12 volt supply or 1.5 volts into two with two cells, 3 volts as a supply, 4.5 volts as a supply. Okay. Therefore, standardization and the availability of standards, etc., and knowing them is very important while you carry out the designs. Then I repeat, design is not difficult, it's very simple. Whatever analysis we carry out, if we do it almost in the reverse direction, it becomes the design, usually, with additional information like what are the systems available for you readily in the market.